let us now look at the second part of the fundamental theorem calculus. Okay, so we know that if I write this, this means area of a particular region, right? This one. All right. So what I can do is I can also change the name. For example, change x to t. Okay. So when you change x to t, make sure you change all x's to t. So now if I want to be a little bit tedious, what we have is, so we can read this as integrate the function y equal to f of t with respect to t. Okay, so what happens is I would have coordinate with t-axis and the y-axis, and then everything else is the same. T equal to a, t equal to b, this is the curve, y equal to f of t. Okay, so what you're gonna get would be the same region, hence the same area. All right, so now you know that the variables that you use inside the integral does not really matter. Just like when we say y equal to f of x, y equal to f of t, y equal to f of I don't know, theta, they all give you the same curves. Okay, so that's okay, right? Now if I make the upper bound of b a variable, meaning it's not fixed constant, so I can have, for example, t squared dt. This would be, what we have in the definite integral. Integrate t squared with respect to t from 1 to 3 versus integrating t squared from 1 to any number that you assign to me. Okay, so what is the difference? The difference is the one on the right is the area of a specific fixed region. Okay, and the one on the right that that you're gonna start from 1 and then depends on the x value. Okay, so now it's like you tell me which x value you want, then I'll find that x value, and then I will give you the area of the associated region, right? So this x can move. All right, so when you have such a freedom, that means here you have a function. When you have x equal to 3, f of 3 is equal to this value, which happens to be the case on the left. However, I can have different x values. I can have x of 1, x equal to 5. In that case, I would plug 5 into the x. So I have integral from 1 to 5 t squared. Then I would have, a different area because it's a different region, right? That's what we mean. So the area that you get from taking the integral depends on the x value that you put inside. So this one on the right, it is a function of x, okay? And we write it as, let's say, f of x. Okay, so a function is really just an assignment, meaning you give me an x value, I give you a associated output value. You give me a different x value, I give you maybe the same, maybe different output value, right? Okay. So the second part of fundamental theorem calculus is saying this. If you have a function defined this way, it is an integral of a given function f from any constant, okay? So this a is any constant to x, okay? So notice that this x and this x are the same x, okay? So you wait for your user to tell you what is the x value they want, and then you put that value into the integral. Okay. So if you have a function defined this way, like, the one we have here, a is equal to 1 and f of t is equal to t squared, and x is on the top. So it's very important x should be on the top. All right. Okay. So if this happens, then the theorem tells you that the derivative of this function is equal to literally just the little f of x. Okay, so for example, if I have f of x defined as like the one we have here on the top, integral of t squared from 1 to x, then according to the theorem, we would have f prime equal to x squared. That's it. This is what it says. All right. So let's look at another example. If I have a function equal to, let's create something that's very complicated. So how about e to the sine of x plus 7x to the power 4 plus 2x. Oops, I don't want x, I'm so sorry. I want to use a different name because x is being occupied already. So sine of t plus 7t to the power 4 plus 2t dt. And this time we have t going from 0 to, the function going from 0 to x. Okay? So make sure that you don't want to confuse the variables that you use for the curve with the x value, where we would be using as the upper bound of the integral. Okay. All right. So this function looks very complicated. But if you look at the statement of the fundamental theorem calculus, it tells you that all you do is you take the integrand and you just write it out, but use x. Okay, so that's what it means. The derivative is equal to the integrand, but using the variable x. That's it. So now every time when you see a function defined like this, as long as the constant is on the bottom and the x is on the top, then all you need to do to find the derivative of such a function is just take the integrand and then use x as a variable. So f prime, capital F prime, is equal to little f.